And welcome to another video. We are going to be doing the Exam 3 review for AP Physics this time around. So let's go ahead and get started. I'll put myself up in the corner. All right, so energy unit. Let's do this. This was an okay test last year. They did okay on this one last year. I think you guys can do better than they did. There were 9 multiple choice questions and 1 long FRQ, 1 lab FRQ, which is an FRQ we really haven't had a lot of experience with. So there's going to be a lot of new things that we learn in this FRQ. So let's go ahead and get into it. I'll start with multiple choice question 1. A block is released from rest at the top of a rough ramp. There is significant friction between the block and the block's speed increases as the block slides down the ramp. So the speed increases as it goes down the ramp. Which of the following correctly indicates whether the total mechanical energy of the block Earth system decreases or remains the same and provides valid justification? So, going through a problem like this, I think it's useful to underline things. Whenever you come across whether there's friction or no friction, underline it because that changes the entire scope of the problem, whether it's friction or no friction. So for this question, we have a block at the top of a ramp, and it goes down, and as it goes down, its speed increases. There is a friction force on the block, and we're looking specifically at the block Earth system, which means that gravity is an energy and not a force. So gravity is not doing work on this box. Rather, this box has initial gravitational potential energy that it's converting into kinetic energy. The net work done on this box has to decrease because there is a force of friction. If we look at the forces on this box, there is a normal force perpendicular to the plane, and then there's a force of friction. Force of gravity is not acting on this box because gravity is being factored as potential energy. It's decreasing, so I would say because of A. There is a force external to the system that is dissipating energy, that being the force of friction. If friction is involved, then there's always going to be a decrease in energy, which means a negative work. Friction always acts as a negative work. Question 2, the figure above shows the net force exerted on an object as a function of the position of the object. The object starts from rest and acquires a speed of 3 meters per second after traveling a distance of 0.090 meters. What is the mass of the object? So we're given a graph of force versus position. So this goes back to my other YouTube video about what are we doing when we're looking at graphs. And for this unit, since it's easier to see it in this unit, but we can get work from this graph. Work is force times displacement, and we are graphing force versus displacement, which means if we take the area under this curve, if we multiply these two axes together, which is the area under the curve, we can get work. How are we going to use work? Well, in this instance, there's no potential energy, so we can just say that work is going to be the change in kinetic energy, and it's going from rest to 3 meters per second. So let's do that. We have a height of 3, a width of 0.9, so the area under the curve is 1/2 times 3 times 0.09, which is the area of a triangle. 5 times 3 times 0.09, which equals 0.135. That is the work, and we know that that equals the change in kinetic energy. So 1/2 mass times final velocity squared, which is 3, minus 1/2 times mass times initial velocity squared, but it's starting from rest, so the initial velocity is 0. So 0.135 equals 1/2 m3 squared. So we can just solve for m times 2 divided by 9 and we get a mass of equal to 0.03 kilograms, which is B. A block is set on a table where there is negligible friction between the block and the table. Negligible friction. The block is connected to an identical hanging block by a lightweight string that passes over an ideal pulley as shown. When the blocks are released from rest, the two-block system gains kinetic energy, so the system includes both the blocks. Which type of force or forces make non-zero contribution to the net work done on the two-block system? So if we look at all the forces acting on these blocks, first thing, Earth is not part of this system. And since the Earth is not part of the system, that means the force of gravity is a force external to the system. So we are now considering force of gravity compared to question 1, where Earth was part of the system. So there's a force of gravity working on the system, specifically working on that block. That is doing work because this system is moving this way, and it is moving in the direction of the displacement. There is no friction, so it's frictionless, so there is no friction acting as work. There's a normal force acting on this block. However, that is not acting in the direction of displacement. It is a perpendicular force, and for work, we want parallel forces. And the tension force is internal to the system, since the tension force is going to cancel out with each other. So if something's internal to the system, it's not causing work. It has to be from outside the system. So it's only gravity that's acting as work done in this case. A. For a sled traveling with a speed of VI along a flat ground, when it reaches a hill, the sled moves up the hill to a flat section of height h, where it has a speed of V final as shown. Friction between the sled and the ground is negligible. What is the sled's final speed, Vf? So I'm going to set up a conservation of energy equation. E initial plus or minus work equals E final. Friction between the sled and the ground is negligible. I forgot to underline that. But what that means is that there is no friction in this case. So I'm not going to consider work done because I'm going to consider gravity as an energy in this case. So initially we have kinetic energy, and then at the final point we're going to have some gravitational potential, and we're still going to have some kinetic energy because we still have a velocity at the end. As a matter of fact, that's what we're trying to solve for. Let's plug in all our variables. 1/2 mass times V initial squared equals mass times gravity times height. They don't use not for initial, they use I, pardon. Plus 1/2 mv final squared. M's will cancel out because it's in every single term. And then we just solve for V final. So 1/2 V initial squared equals GH plus 1/2 V final squared. 1/2 V initial squared minus GH equals 1/2 V final squared. Multiply everything by 2. We get V initial squared minus 2GH equals V final squared. And lastly, we get V final equals the square root of V initial squared minus 2 times G times H, which should be one of these options, and it is. It's B. An asteroid is moving directly toward a planet as shown in the figure. At a later time, as shown in figure 2, the asteroid is closer to the planet and still moving directly towards it. The change to the planet's velocity is negligible. Which of the following correctly describes the change in the total mechanical energy of the asteroid planet system and the change in the kinetic energy of the asteroid between figure 1 and figure 2? So I would say energy is conserved in this case. I don't notice any forces from acting in external to the system. Energy is conserved. However, I would say that the asteroid is moving faster in figure 2 than it is in figure 1 because its kinetic energy is going to be increasing. That is because as it gets closer to the planet, its big G gravitational potential energy increases in magnitude. As we go down in distance, we increase in force of gravity. And since this is a negative, that means we need that's supposed to say constant. Since this is negative, if this gets bigger, and since it's a negative, that means this also needs to get bigger in order for energy to be constant. So the answer there is B for number 5. A car of mass 1,300 kilograms is traveling on a highway at a speed of 25 meters per second. A car passes a truck that is moving in the same direction at a speed of 15 meters per second. From the perspective of an observer on the truck, what is the kinetic energy of the car? So this has to go back. This goes back to Unit 1 when we did relative velocity. The relative velocity, so the V relative, which is what we're going to base this off of, is just the difference between the velocities. 25 meters per second minus 15 meters per second, which is 10 meters per second. The kinetic energy of the car with respect to someone on the truck, the car is moving 10 meters per second faster than the truck. So the kinetic energy with respect to someone on the truck is going to be that difference in velocity. We're going to take that difference in velocity to factor that out. So kinetic energy is 1/2 mass times velocity squared, which is 1/2 times 1,300 times 10 squared, 1300 times 0.5 times 10 squared, and we get 65,000 joules, which is B. A force of magnitude F is exerted on a block along a horizontal surface over a distance of D, doing work W1. The force is exerted at an angle of 30 degrees above the horizontal, and there's negligible friction between the block and the surface. Another force of magnitude F, so the same magnitude, pushes an ideal block along the same surface over a distance D, but the force exerted at an angle of 6 degrees above the horizontal. The second force does work 2, the first force does work 1. What is the ratio of work 1 to work 2? So work is force times distance, specifically the parallel component of the force times the distance. So we're only looking at this component of the force, not the entire vector itself. Only the component of the force that is in the direction of motion, which is specifically going to be the cosine component. So this is F cosine of 30. This one is F cosine of 60. From the get-go, I can see that this one is doing more work than this one because it has a bigger component of the force vector going in the direction of motion. The bigger we make this angle, the less work that gets done because the more of our force is being pulled up instead of in the direction that this box is moving. So since we're ranking work 1 to work 2, we know that the work 1 should be bigger than the work 2, which means D is out because D says the work on 2 is bigger, and C is out because they're not the same. One is going to be bigger than the other. It's between A and B. To find the ratio, it's just going to be a ratio of the cosine of 30 to the cosine of 60. When we simplify everything, technically it's FD cosine of 30 to FD cosine of 60. That's the ratio of work 1 to work 2, but the force and the distance are the same. So I don't know trig ratios off the top of my head like some of you, so I will use a calculator. So the cosine of 30 is 0.866. The cosine of 60 is 0.5. So 0.866 to 0.5. I'm going to multiply both of these by 2. So I get 0.866 times 2. 1.732 to 1 is the ratio. And 1.732 is the square root of 3. So it's that ratio right there. 8. In each of the figures shown, a motor pulls identical blocks up a ramp at the same constant speed Friction between the blocks and the ramp is negligible. Which of the following correctly compares the instantaneous power delivered by the motor at the instant shown in the figure? So if we go back to our equation sheet, so where's my equation sheet? Right there. We have an equation for instantaneous power. Instantaneous power is force times velocity. So the faster something is moving, the more power that's being put into it. And the greater the force that's being put onto an object, the more power that's instantaneously being put onto it. That kind of checks out, right? The more we push something, the more power. The faster we push something, the more power. So going back to our equation, all of these are moving at the same speed. It said that same somewhere. Oops. The same constant speed. So if we're comparing the powers, it's just going to be a ratio of the force that's being put onto this block. I can see that figure 3 has the least amount of force because this angle is the most shallow. These angles look the exact same. If we look at in other words, we're really just looking at the slope of this ramp. We go over 4, we go up 4, we go over 2, we go up 2, and for this one we go over 7, and we go up 4. So both of these are moving with a slope of 1. This one's moving with a slope of 4 over 7. Is it 7? That's a weird number. So that means these two are both going to be operating at the same instantaneous power. This one is going to be operating at a less instantaneous power. So P1 equals P2, which is greater than P3, which is B. P3 is the most shallow. Now, if we were to compare like the overall power put into this, then maybe we would also need to consider the distance that these blocks are being pushed. But that's not what this question is asking. This question is just looking at the instantaneous power. That's the difference between the two. We don't care about how far these blocks have to travel for instantaneous power, just like how much power we need to put at them at any given moment. All right, last multiple choice question. A person exerts an upward force on a box as shown above. The box may be moving upward, downward, or not at all while the person exerts an upward force. For which of the following motions of the box is work done by the person on the box correctly indicated? Okay, so we're basically having to go through each of these one by one and see if it makes sense. So first let's look at what's happening with this box. We have a force exerted, that's a bad arrow, let me try that again. We have a force exerted by the person going up. We do not know how big this force is. And then we have a force of gravity going down. We do not know how big that force of gravity is. It can be the force the person pushes can be bigger than force of gravity, or we can have something where the force of gravity is bigger than the force of the person, or we can have something where they're equal and opposite and it's moving at constant speed. If it's this one, or actually let's just keep going, but keep in mind it can be any single one of these options right here. So A, if the motion of the box has no motion, then the work done by the person on the box is positive. That is not true because work is force times displacement. If we do not have a displacement, we cannot say that we put work into this object. So, because that means we don't have a change in kinetic energy because it's not moving, and we also don't have a change in potential energy because it didn't gain an elevation. We need one of those two things, thinking about it in terms of force being change in energy. B, the box is moving upward with a decreasing speed, and the work done by the person on the box is negative. So in this case, upward with a decreasing speed means that gravity is bigger than the force of the person, but the displacement is still this way. It's still moving upwards, which means the work done by the person is still going to be positive. because work is not dependent on the direction of acceleration, which is downward. It's dependent on the direction of the displacement, which is upwards. So it's going to be a positive work. Downward with constant speed, work done by the person on the box is 0. So constant speed means they're both equal and opposite, but we're moving downwards. That's the direction of the displacement. The work in this case is going to be negative because our force is pushing up, but our displacement is down. Even though that they're equal and opposite, we're just looking at the work done by this force right here. So it's also it's not B, it's not C, which means it has to be D. Moving downward with increasing speed, so that means the force of gravity is bigger than the force of the person. The work done by person on the box is negative. That's true because our direction of displacement is down, which means our work has to be negative since our force is pointed up, opposite to the direction of the displacement. That is answer choice D. All right, let's move on to the FRQ. So lab FRQs, I haven't given you one of these yet. I've been very kind this year. I haven't given you a lab FRQ. So we're gonna learn a whole lot of new things really quick in this lab FRQ. But in my opinion, lab FRQs, these are the best ones. These are the best FRQs. There is a lot of very, very achievable points in lab FRQs, even if you are unsure about everything to do with the physics. You can get a lot of points in lab FRQs if you just stick with it and do things consistently. In an experiment, students are to calculate the spring constant K of a vertical spring in a small jumping toy. Ooh, maybe one of those toys that looks like this. That initially rests on a table. When the spring in the toy is compressed a distance x from the uncompressed length L naught, then the toy is released. The top of the toy rises to a maximum height h above the point of maximum compression. The students repeat the experiment several times, measuring h with objects of various masses. So various masses taped to the top of the toy so that the combined mass of the toy added to the objects is m. The bottom of the toy and the spring each have negligible mass compared to the top of the toy and the objects taped to it. Okay, so we have an experiment where we're basically launching a toy, we're measuring how high it goes, and we're in the process of doing a lab that's a lot like this, but I gave you a lot of different directions to go with the lab. In this particular lab, they're measuring height and they're changing the mass of the object by taping different masses to like the top. They're adding mass to the top. So they're altering the mass of the object. I know a lot of you, when you did this lab, you decided to alter the compression. But you also could have done this lab by altering the mass. So that's what this person is doing. Derive an expression for height in terms of m, k, and x and fundamental constants. So I am going to do a conservation of energy. I'm going to set up a conservation of energy. And the 2 points I'm going to look at is while the spring is compressed at the start. So we're going to call point 1. And at the max height, point 2. While the spring is compressed, it has spring potential energy. It does not have kinetic energy. It does not have potential energy. It's still on the table. There is no work done on the system, so let's move on to the other side. While at the apex of the flight, it no longer has spring potential. The spring has been uncompressed. It does not have kinetic because at the maximum height, the velocity is equal to 0. But it does have gravitational potential at the max height because it has a height. So let's plug these in with their respective equations. 1/2 kx squared equals mass times gravity times height. And we need to solve for height. So height is going to be equal to kx squared over 2 times mass times gravity. That is our expression. let me flip over to the FRQ. For this question, 2 points. 1 point for starting with the conservation of energy, 1 point for the final answer. With the spring compressed a distance of 0.02 meters, in each trial, the student obtained the following data for different values of M. Okay, I did make an error when I printed this FRQ. There's not supposed to be an extra 0 here, so we're gonna pretend that there's no extra 0 there. That's a my bad when printing this and copying it over. Based on the equation derived in part A, what quantities should be graphed so that the slope of a best fit straight line through data points can be used to calculate the spring constant K? Okay, so when we have these lab problems, and we're always going to be having to graph something. We're always going to be having to graph something and make it so that when we plot a line of best fit, the slope of that line of best fit can be used to calculate our variable. So here's what we do. First, let's look at the equation. Now, most types of these FRQs, they split up the deriving part from the actual lab part. So they will already give you the equation that you're going to base this off of. In this one, we're just going to use this equation right here that we derived. I'm going to separate all of my constants from my variables real quick. So actually, first thing I'm going to do is I'm going to solve for K, since K is ultimately what we're trying to get. We're trying to find the spring constant K, so let's solve for spring constant K. K is going to be equal to 2mgh over x squared. Now let's just subtly separate my variables from my constants. In this lab, the way that this is set up, height and mass are not constants. Everything else is a constant, the compression, gravity, and then that 2. So let's do this. 2g over x squared times m times h. So what that means is I need it so my slope gets mh. That's a little bit tricky to think about, but what we're going to do is this. If we graph, let's say, h versus 1 over m, if we graph h over 1 over m, we have h on the y-axis, 1 over m on the x-axis. Then my slope is rise over run. So the rise of the line is going to be h. The run is going to be 1 over m. Dividing by a fraction means multiplying by the reciprocal. So h over 1 over m is the same as hm, which is what I want to find k. That's what the k expression implies. So these are the correct axes. You can also do this with doing m versus 1 over h. Same thing, if we do m versus 1 over h, now we have m on top, 1 over h on bottom, and we still end up with m times h, which is what our equation of k needs to happen in order to solve for k. So we're going to graph, let's pick this first one. We're going to graph h versus 1 over m. Actually, let me pick whichever one I did. I did do h over 1 over m on the answer key. So the reason that they give you extra columns is so that you can derive things yourself. So I need 1 over m. I don't just need m. So we're going to make a 1 over m axis, which is going to be 1 over kilograms in units. So 1 over 0.02 is 50. 1 over 0.03 is 33. 1 over 0.04 is 25. Don't like that, 25. 1 over 0.05 is 20. 1 over 0.06 is 17. And now I'm going to ignore this axis. I'm going to grab this one and this one. Fill in one or both the blank columns, and we did that. Oops. Let's go graph. On the axes below, plot your data and draw a best fit straight line. So we need to make a graph of a line of best fit before we need to do that, we need to make the graph. So to make the graph, we said that we're going to graph h, the height, which is in meters. It needs to be in meters. If they give you compression in like centimeters or millimeters, you need to convert to meters. And we're going to graph 1 over m. The units is 1 over kilograms. Looking at my data, h goes from 0.49 to 0.18. So let's just take it in like into tenths. So let's start at 0, make this 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Make sure your range includes all of the points. For mass, it goes from 17 to 50. So I'm going to again just start at 0 and work my way up by tens. I think that's appropriate. So 10, 20, 30, 40, 50, 60. Most of the time, your graphs are going to start at 0, 0 on the x and 0 on the y. When it doesn't, usually they will actually give you that on the graph. It won't start at 0, but like they will tell you where the 0 is. Okay, now we graph. The first point is 50 and 0.49. So 50 and 0.49, I'm going to say is right there. Then we have, I'm going to cheat, I'm going to look at the answer key here. 33 and 0.34. So 33, this is 35, 32, 33, and 0.34 is right here. 25 and 0.28, 25, 0.28, 20 and 0.19, so we have 20 and 0.19, and lastly 17 and 0.18, 17.18. All right, we've graphed off our points. Time to make a slope of a line of best fit. When you do this on an actual test, please use a ruler. Don't make a squiggly line of best fit. That's not a line. You are allowed to bring a ruler or a straight edge for this exact purpose. I'm going to cheat, and I am going to use one of these. So I'm going to start at 0, 0. Something like that. All right, that is our graph. I'm going to go over the point value totals of all these at the end. So let's continue. Using your best fit line, calculate the numerical value of the spring constant. So this is going to require us to take the slope. Remember, the slope is what we designed this graph to do. The slope is change in y over change in x, or rise over run. We need to pick 2 points. And I like to always make 0, 0 one of my points because 0, 0 is on that line. Looking at another point on this line, I see that this point falls right on my line, so let's use that point as well. That is the 33.034. So y2 minus y1, y2 is 0.34 minus 0 over x2 minus x1. x2 is 33 minus 0. And we get 0.34 over 33. 0.34 divided by 33, which is 0.0103. The units is meters over 1 over kilograms, which is just meters times kilograms. You do need to show the slope calculation. Listen, calculating slope isn't the most complicated of equations, but they do want to see that you're actually putting down the equation there. Last thing, describe a procedure for measuring the height. Oh, wait, no, we need to, actually, we just found the slope. We need to go and find the spring constant. Okay, the spring constant, k was equal to 2 times g times x squared times mass times height, which means we're going to do 2g over x squared times our slope, since we said that our slope is mass times height, right? Man, I don't like that. Move back over here. Our slope is a mass times a height, which is in meters times a kilogram. So 2 times gravity, 9.81, over x squared. The compression was somewhere over here. What was the compression? 0.020. So 0.020 squared times our slope, which is 0.0103. And we get 2 times 9.81 times 0.0103. Divide that by 0.02 squared. And we get 505.215. And the units of a spring constant are newtons over meters. There's our answer. For these questions, usually they have an accepted range. I don't know what the range is with this particular question, but that is definitely going to fall in the range because they do understand that a lot of it is based off your line of best fit. Okay, next, last one. Describe a procedure for measuring the height in the experiment given the toy is only momentarily at that maximum height. So we need to describe a procedure for getting that height. So when that toy reaches its maximum height, how can we exactly find out what that height is? I'm not going to write out the entire procedure, but I have two good ways. One, we can set up a slow motion camera. A slow motion video recorder, and then specified that we have a ruler or a meter stick behind with a meter stick behind. And what that allows us to do is, why this is tough to do is because it's really hard to see in real time when that object hits the max height. But if we have a slow motion camera, which it doesn't say we don't have a slow motion camera, maybe we do have a slow motion camera, it makes that easier to look back on that playback. The other thing we could do is we can set up a flat surface perpendicular and make small adjustments. Over a lot of trials. So what I mean by that is when we launch this thing, what we can do is we can set up like another meter stick this way, and then we can continually lower or raise that meter stick until it's right at that max height, and it's just barely touching the meter stick every single time. That way to know that's the max height that it's reached, and that also eliminates the human error of just like seeing where it is at that moment in time. And we also don't need a slow motion camera. There's probably other ways you can do it, but those are two ways that I thought of. And with like writing procedures, there's usually multiple ways that you can get a laboratory done. What the physics graders are looking for is if it just makes sense. Okay, I want to go back and look at point values with this FRQ because this is really, really insightful. This isn't a perfectly aligned lab FRQ, by the way. We're going to look at those after this test. But going back to the point values, for this one, there was 1 point for picking the correct axes. Fair enough, that is kind of tricky to do. You have to like conceptualize this equation pretty well. But going to the graph is really interesting. For the graph, there are 4 points with this graph. 1 point is for the axes, linearly scaled. with units plotted. So if you got the axes right, if you made good axes and just plotted the data correctly, you don't need physics to do that. You're just plotting the points that already are there, then that's a point. You got a point for the labeling the axes, units on the axes. Again, that's just taking what you're given here and plotting it over on the graph. If you got that previous part wrong, they don't mind if you got that previous part wrong because continuation points exist, but you just have to plot it as there is with units and labeled correctly. You got a point for just a line of best fit. Line of best fit. You got a point for just making a line of best fit, drawing your best line of best fit. So that is going to be as it is on the exam. You get a point for drawing a line of best fit. And last thing was for plotting the points correctly. So if you took these points that you made, whether they're correct or incorrect, if they're incorrect, you would have gotten points off on a previous part. But if you took those points and plotted them correctly on this graph, that is another point. There are 4 points associated with this graph, and this is why these are the best questions in my opinion. There's 4 points associated with this graph, and you don't really need to know physics to do any of them. They're all just basic like math graphing skills. Plotting a point, making sure the axes are labeled and scaled, making a line of best fit, putting down the units that you already know. That's it. If you do those 4 things, those are 4 easy points. For part D, there's another 2 points. 1 for taking the slope of your line of best fit. That's not a physics skill, that's just a math. You did that in Algebra 1, doing slope, rise over run. If you just take the rise over run of your line of best fit that you already got a point for, then you get another point if you took that slope correctly. The second point is for actually using the slope to find K. Which, fair enough, that is a little bit more of a challenge to do, and that is based off of can you manipulate a physics equation correctly. But 1 point for slope, that's pretty nice. And then this last one, it's 1 point for the actual procedure itself. So just going through this graph, I would argue, so this whole FRQ, 2, 1, 2, has 10 points associated with it. And I would argue like 6 of them, you don't need to know physics to get these points. Let me pick a different color for a second. One of the points was for starting with conservation of energy. Not getting the right answer, just starting with conservation of energy. You got a point. You got all 4 of these points for the graph, which are just graphing skills. You don't need to know physics to know how to graph something. Whether or not the graph is correct, those are tested elsewhere, but you can get points just for graphing things correctly and doing a line of best fit. And lastly, you got another point for just finding the slope of your line of best fit. That's 6. That's 6 of the 10 points that are just based off that are minimal physics knowledge points. Now you do need to know physics, and you know how to have a good understanding to get all of the questions correct. But if you don't know if you don't know how to analyze all these questions, if you're someone who does often panic when you get to an FRQ, you can still make your way through this FRQ and do well on it. So don't freak out when you see something like this. All right, that concludes the exam. I just decided to do the FRQ and multiple choice in the same video. I'm talking, but you can't see me. I hope this video was good. I hope you do on your exam. Focus. I hope you do well on your exam on Wednesday. Ask questions, you have questions. And that is it from me. So, all right, bye. See ya.